Well, welcome everybody to this Synopsis webinar. Thank you so much for joining us today. My name is Simon Richards, and I'm part of the go-to-market team here at Synopsis. I've been working with the Simpleware product for over a decade, and we're really looking forward today to presenting to you an exciting announcement. So we're going to be taking a look at the Simpleware University Bundle, which has recently been launched by the Simpleware group within Synopsis. And our title today is Empowering Academia to Do More with Medical Imaging. We hope you really enjoy what we're presenting to you today. So as I said, my name is Simon. I'm going to be joined a little bit later by Associate Professor Dana Carpenter. We're really delighted to have him with us, and he's going to be presenting on some of his research and teaching that the Simpleware software has been used within. So if you're unfamiliar with GoToWebinar, you should just have a box on the right as indicated on my screen. You're all in mute mode at the moment. If you do have any questions, we'll do a Q&A towards the end of our session. Please put those in the toolbox. And again, any other questions, please put them in there. So here's our plan for our time together today. I'm going to give a presentation shortly. You'll be able to submit questions, which we'll take after I've presented and Dana has presented. We'll try and get to as many of those as we can, but if we're unable to, we'll try and respond to those via email after the presentation has finished. And do keep in mind, we're going to record this, so that'll be available for download afterwards. And we would love it if you would, if you found this content useful, if you could point colleagues or fellow researchers to this resource. That would be fantastic. So allow me to begin with the Simpleware University Bundle. This is a newly launched product from Simpleware, and it contains the entirety of the Simpleware software suite, and we're making that available at scale and at low cost to academic institutions. So here's our announcement. We are delighted to announce the arrival of the Simpleware University Bundle, and we truly believe this is going to be a game changer for academics and researchers working with 3D and medical imaging. We've got special thanks to give to those who've made this possible. So we'd really like to thank the Synopsis Academic and Research Alliances Group. That's the team within Synopsis that takes Synopsis products and make them available to university and academic institutions. So thank you to that group. Now, we're joining the Simpleware product is joining the Synopsis University program. This is a huge program that enables the 200 plus microelectronics softwares, curriculum, resources and support to be made available worldwide, and Simpleware is now being made available through this university software program. So thank you to them. It's being used, this university software program is being used globally at the moment with an impressive presence across the globe. And we hope to see a similar level of take-up of the Simpleware University Bundle. So let me get straight to it and tell you what it is before we get on to hearing about the software itself. So what it is 50 full research licenses that are made available to your institution. There are no feature or functionality limitations, no technical or export limitations. It includes some really exciting tools, AI-enabled auto segmentation, and I'll give you a few examples of that a little bit later. The licensing itself, how it works, it's distributed as a floating or network license. So it's a server with multiple client machines. That allows it to be shared across campus. And our vision for it really is that it would be lowering the barrier of entry to 3D image-based modeling. So we can see this being a valuable resource for both researchers, but also incorporating into teaching courses, perhaps master's level biomed, 3D imaging, or even simulation courses. The software itself comes with some really high quality tutorials and example data such that the learning curve for you and for your students isn't too steep. And the purpose of this university bundle is really for the final output to be peer-reviewed fundamental research. So just to be clear, this isn't for commercial purposes, but solely for academic purposes. Currently, in terms of its availability, it's available in the Americas, Europe, Middle East, and Africa. Not yet available in Asia Pacific, but we're working with partners to really try and reduce barriers to entry in those places as well. So that's a brief snapshot at the outset of what the Simpleware University Bundle is. So just to set the scene, if you're unfamiliar with the field or with Simpleware, what we're trying to do is enable people to do more with their 3D medical imaging data. So the starting point is typically MRI or CT imaging, and we're going from that through to segmentation, so picking out the regions of interest, and then generating models that are ready for simulation, 3D printing, and further downstream applications. That's the field that Simpleware is applicable within. So doing more with that CT and MRI data, going beyond visualization to segmentation and modeling. So what does it do? What are the functions and the tools within it? If we work our way around the clock here on this slide, if we start at the top, it's importing and visualizing 3D and 4D image data, performing in a number of different ways, from highly automated through to semi-automated through to manual, a variety of different segmentation and processing steps to pick out your regions of interest. The step once you've generated your segmentation is then to perform valuable measurements and analysis. They can be very useful for steps downstream, such as surgical navigation or planning. The box at the bottom of the clock there is how we enable the integration of objects from the world of design. So introducing CAD geometries and implants or medical devices into this image-based model. And then this step here where you can see the human head, that's model generation, where you take that composite model both from the image world and from the world of design and create a multi-part watertight mesh that could be used for simulation, or the surface itself used for 3D printing. And all of that is undergirded by some really robust scripting and automation possibilities. So the entirety of the tool is scriptable with a very useful and interactive API, and that's in Python and C#, enabling you with the tools in front of you there to do levels of automation, batch processing, or just activating Simpleware from the command line that wouldn't necessarily be possible with other 3D image-based segmentation tools. So that's covering what does it do. Now, if we think more about the areas in which this tool would be relevant and in which it applies, we kind of see these, at least in the medical space, in these three tiers. So if we have a look at those images on the right of the screen, having worked our way through this arrow of the workflow from imaging, segmentation, model generation, analysis and reporting, what could we do next? Well, we would be enabling application areas as diverse as implants, surgical guides and surgical planning, through to actual simulation, so R&D simulation, or as we see the interest in this building and building, in silico trials, and that final image at the bottom, truly generating a 3D print ready model. So being able to go from CT and MRI through to a 3D print ready file. And we do that using all within this one interface, and that 3D print step is done using a 3D printing toolkit. And overall, folks are considering the Simpleware tools to be best in class for image processing, for manual to AI-enabled automated segmentation, for full customization, and for exporting to a variety of different contexts for downstream use. The group as a whole, you've met me today. My name is Simon. I'm based in the UK, and I'm part of the go-to-market team. But we have a global presence. We have dedicated sales, support, and service teams. Really, the area I'm speaking into today is the clinical and the life sciences, but we also have applications in materials, manufacturing, and more. Anything really where you're working with 3D image-based modeling. So allow me just to cover what is within the Simpleware University Bundle. And this is the bit that I really like doing with potential users, because we are making available really the entirety of the Simpleware software suite. And the only bit that isn't available is the fact that this won't be medical regulatory cleared. So it's not 510K cleared or has MDR clearance. That's the only thing really that isn't being provided in this university bundle. So you'll have access to the full set of image processing, auto segmentation, and surface tools within the Simpleware University Bundle. You'll also have access to the full suite of volume meshing tools, measurement tools, and everything that you would need to generate a 3D print ready file. So I think you'll agree it really is a powerful bringing together of many different tools in this one user interface that's really going to enable some great teaching and research to be done, and we hope to really accelerate usage in this field. We see a steep growth in the usage of these tools in the open source world, and we would love to really foster and grow that usage further with these robust tools being made available through the Synopsys University program. So we're regularly developing and adding to this product. I'm just going to run through one or two new features that are new as of June 2024. So we have added into the software recently the ability to generate surgical cutting guides. We have included into the segmentation space an AI-enabled bone filling tool, and also a mask similarity calculator, enabling you to compare two masks. Then further developments in our auto segmentation suite of products. We've brought in a hip revision CT tool, allowing you to generate models where there might be a large amount of metal artifact or metal noise, and also an AI automatic segmentation for the spine CT. This is incredibly powerful and a new area of anatomy for us for our auto segmenters, and some improvements to our knee CT auto segmenter. So that's what's new as of June 2024. Here's just a few images to show these things in action from left to right with the AI enabled bone filling, which intelligently solidifies masks created from the threshold or split operation. Here's our auto segmentation of hip revision cases in action. Here you can see from left to the middle our hip CT tool, but then this new hip revision CT tool accurately enabling you to capture the implant itself and with reduction and removal of noise. And our CT auto segmentation of the spine tool. All of this is nicely documented for you in the Simpleware software, so you'd be very welcome to try an evaluation license. We have a large number of tutorials that are searchable and available within Simpleware, and all of the data for those is available too. This makes the learning of the product relatively easy. There's also just a very large help guide, again keyword searchable, that can help you as you are learning the tool for the first time. Well, that's what I wanted to bring you really about the Simpleware University Bundle, but more importantly, we want to hear about how it's going to impact and how it's going to be used or has been used in academic research. And for that, we're going to turn to our friend Dana Carpenter, who's with us today. Thank you, Dana, for joining us. And I'm going to just introduce Dana, and then Dana's going to give us an overview of some of his work at UC Denver. So Dana received degrees from Georgia Tech and Stanford University, and after working as a postdoc researcher engineer at UC San Francisco, he joined CU Denver in 2011 to combine medical imaging and biomechanical simulations. If you ask him, he thinks he might well be the first Simpleware customer in the US. Over to you, Dana.
Thank you, Simon, and thanks for having me here today to talk about how I use Simpleware. I have been a faculty member here at CU Denver, as you said, since 2011, and I purchased Simpleware with my startup package to get my lab up and running, and I've been using it ever since. So I've been using it in my lab that whole time, and then in my classroom almost that entire time. My first class that I taught was my biomechanics class, and that had some Simpleware in it from the very beginning. So happy to be here today to just share a little bit about how I've used it and how I'm going to proceed to use it in the future now that the University Bundle is available. So I got the University Bundle last summer. I got my license, and so it's already allowed me to do more. So happy to show how that's unfolded over the years. So just to orient everybody, I'm at the University of Colorado, Denver. So we're part of the University of Colorado system. We have 4 campuses, flagship campus in Boulder. We have a campus in Colorado Springs, about an hour south of Denver, and then the Anschutz Medical Campus. My campus is right downtown. You can see in the pictures here. This is the building where my lab is, but we have close ties to the medical campus as well, and that's really what attracted me to come in to do my academic work here, is that I could have the resources of the hospital, medical imaging resources, physicians to work with, but also I'm a mechanical engineer by training, and so I could be at home in a mechanical engineering department. So, and that was a kind of a natural fit for the type of research I do. So today I'm going to talk about primarily how I've used Simpleware in the classroom, but then at the end I've also got a selection of research projects to show other ways that I have used the software over the years. So the main way that I use Simpleware in the classroom is as part of our Master of Science in Mechanical Engineering biomechanics track. That coursework I've got listed here. You can see the first 2 here, biomechanics and advanced biomechanics. That's primarily where I've implemented this in the past. I had 2 node-locked Simpleware licenses for many years, and so I would create content for the classes with those and actually assignments, but the students, just based on scheduling and limitations on the number of seats I had, that the students really didn't get hands-on training in the software. I just showed them how it worked, and then they could actually use it for projects once we, but everybody working on one homework assignment all at once wouldn't work out. But now the university bundle is going to allow me to actually have the students, instead of me just handing them a finite element mesh, let's say, they're going to create their own this coming school year. So I also teach finite element analysis, and again, now given the university bundle's capabilities, planning to implement some scan IP in my FEA class as well. And I also wanted to point out, this is a part of our graduate program, but these two courses, and actually finite element analysis as well, are available as senior level technical electives to our students. So I have usually the class is about half and half, seniors and then graduate students. So in my biomechanics class, first, before we get to the modeling, I teach the students about different ways that we can get images that we can use to create models. That's primarily medical imaging, CT and MRI, as well as micro CT, which I guess is more of a research tool than really clinical. The vast majority of what we do is CT and MRI, and really these days CT, just based on the studies that I'm involved with at the moment. But I've also used Simpleware to process confocal microscopy images. So if you're not familiar with that, it's a microscope that can give you a stack of images at different focal distances. And so it really gives you, very similar to a CT or MRI scan, a stack of images that you can then put together to create a 3D image. And I think I might have blown my integrative biologist's mind the first time I showed him the image that I created from Simpleware. He had never seen a 3D rendering of, this is his microscope, but I used it in a different way than he had ever seen. We also have used Simpleware to create models from 3D surface scanning. You can see in the bottom right corner here, one of our graduate students, she was scanning in a baseball for a biomechanics project that she was actually created a 3D printed instrumented baseball to track accelerations during pitching. And then in the bottom left here is a micro CT scan of a porous polymer that we investigated in our lab as well. So I teach the students about all these imaging capabilities, and then I teach them how you can take that image and create 3D models, whether it's for 3D printing or for finite element analysis or whatever your needs are. So one of my lectures focuses on segmentation techniques. I show them, this is a cube of porous polymer scanned with micro CT and then segmented with thresholding in Simpleware, which is the most simple of segmentation techniques. So I show the students, you can just by accepting a certain range of brightnesses in the image, we can get a 3D model. But that's fine if you're going to calculate things like volume, things like that, porosity. But as you can see in this image, there are some little floating pieces around here because of the sides are cut off from the rest of the structure. And so I then show them how we can use more sophisticated segmentation techniques like the background flood fill region growing algorithm in Simpleware, which then creates a fully connected 3D structure. So it still uses a threshold to accept a certain range of Hounsfield units or brightnesses in the image, but it eliminates those little floating pieces. And so I've just got an overlay here of the blue pieces that are left are the little islands that got eliminated by using the flood fill technique instead of segmentation. And this gives us a fully connected structure that we can then mesh and in the meshing tool in Simpleware and export to finite element analysis software. We use Abacus in my lab, but I know that Simpleware is able to export in other formats as well. I also show them how to create a model of a femur, and then I actually take the mesh that's created from this, and that's given to them as a homework assignment to go in and do a finite element analysis on. If you've used Simpleware in the past, you might recognize this scan. It's from their tutorial. So as Simon said, there are a lot of good tutorials, and that's anybody that works in my lab, that's usually the first thing that they get assigned to do is work through those tutorials. And when I started teaching my class, because of the tutorials and the data that were there, I automatically had content for my class that was valuable to the students, show them how model creation takes place, and then actually hands-on use the resulting mesh to do finite element analysis in the biomechanics class. This this is going to be better now that there's the university bundle, because now I'm going to have them do this themselves. So I used to just hand them the mesh at the end, but now the students are all going to be able to be in the lab at the same time with me instructing them and actually create their own models using the university bundle. So I show them, here's the first step of segmenting a femur is to threshold it. And then we use closing operations to eliminate all the little, I can go back and forth. You can see all the cavities that got filled there. We actually then use the cavity fill tool, which will fill up any cavity that that doesn't communicate with the outside of the bone or the outside region. And then we create a 3D mask and smooth that using Simpleware, and then finally create our finite element mesh. So for this, I used the FE-free adaptive meshing algorithm. Again, this is straight out of the tutorial, and it gives you, in this case, the model that I've always used over the last 12 years or so had just under 10,000 nodes, because our academic version of Abacus is limited to models of 10,000 nodes or less. And so this allows the students to actually take this mesh and go analyze it in the computer lab with finite element analysis. And I have them do a couple different loading configurations and look at how loading affects stress distribution in the proximal femur. And then I show them, how this adaptive meshing algorithm works, where we get larger elements in areas where there's not as much change going on or not as much curvature, and then a much finer mesh in regions where we need more detail, and actually go into that a little bit and talk to them about mesh refinement and show them this example of using the refinement tools within Simpleware. So here's that initial mesh on the left with the 43,000 elements or so. And I was like, well, what if you want to gain more accuracy? What if you need more detail? Well, you can do a global meshing with a much finer mesh size, and that gives us a much bigger mesh of 329,000 elements. But I'm like, well, what if you're really interested in what's going on, say, at spots where muscles connect, like the greater trochanter and lesser trochanter, and we can get away with less detail other places. You can use the tools to actually spot refine the areas where we're really interested in, and that allows you to get much more detail, a much finer mesh in regions where you want it. But now we're at a mesh of 79,000 elements instead of 329,000. So allows you to save a lot of computational time and computational resources that way by using those mesh refinement tools. And so using this mesh, and then also there's another tutorial where you use the CAD integration tools within Simpleware to combine a computer-generated hip implant into the proximal femur. And so I have two different homework assignments based on these meshes. So the first, as I mentioned before, was that just analyze an intact femur in a few different loading situations to look at how stress changes as the load changes direction, say during if you were to take a step at walking versus if you were to fall down onto your hip as it hit the floor. And then I also do they then compare that to once they put this hip implant in, and they have to go in, and I have them find the material properties of bone, find the material properties of titanium implant. Actually, I have them do a couple different stainless steel, titanium, and PEEK, polyether ether ketone implant mechanical properties, and so that they can look at the effects of the implant mechanical properties on stress distribution as well. And so that's how I've done it in the homework assignments. Then the students have the ability, or they have the ability, the students have to do a project. And so it doesn't have to be a project using 3D images or finite element analysis. I allow them to do any kind of biomechanics project they want, but just because of the nature of the class and what I teach them, I'd say at least 2/3 of the students in the class end up doing something along these lines. So some sort of patient-specific implant, something like that. And so I just wanted to show a couple of examples of projects that students have done in the last couple of years. This was a group of undergraduates that you can see here. They were looking at reverse shoulder arthroplasty. So this is a surgery that takes the native shoulder anatomy. You can see here the humeral head, that's the ball and socket joint, although a very shallow one of the shoulder, and reverses that and actually puts the dome-shaped implant onto the proximal side of the joint, and then the socket on the actual limb. And so these students created this model using Simpleware, and then they did a finite element model, and they also did a 3D printed model as well for the class. This is a graduate student project, so a little bit more advanced. In this case, she designed, this is a student named Kathleen Badillo. She created a hip implant, a short stem hip implant with these different dimple configurations that you can see here that allow bone to grow in and possibly secure the hip implant in place more securely than a typical cemented implant. And you can see here she implanted that into the bone. For each different implant, she did a couple different positions, and she did a really thorough finite element analysis of these implants to try to kind of optimize her idea for this hip implant design. You can see here just a little bit more detailed information from her report from the class, where she shows the different components of the model. She included bone marrow, a layer of bone cement, and then the bone and the metal implant as well. And so she was able to put together a pretty nice model, just with the experience that she had in the class. And so that's basically a summary of what I've done teaching. And then just for the end here, I wanted to give a few examples of how we've used this in my lab as well. And this is just a picture of our lab, some of the students I've had over the years. You can see actually, I guess these two of these computers. This is a Simpleware working on a hip, as you can see in the image. If you kind of squint your eyes, you can see it. And then here is a finite element model of an ankle implant. We created that model in Simpleware and then exported that to Abacus for analysis. And I've actually got a little quick video of that one in a minute. My lab also does some experimental work to both complement our modeling work, so whether that's to validate models or to give us input to the models if we actually need to measure properties to go into our models, for example. So that's the Smart Materials and Biomechanics lab at CU Denver. And so just to show you a few quick examples of what we've done in the lab, we've looked at a lot over the years, intramedullary nails, specifically for ankle fusion or talotibial calcaneal fusion. We've done models of lumbar fusion devices and hardware, and we've tried to match those with experimental models. You've seen already a couple pictures of this porous polymer that I have a colleague that we got hired at the same time, and he's a polymer specialist. And so we worked together on ways to both experimentally measure and then simulate the behavior of different types of polymers. And then this is the image that I mentioned before that the biologist was so impressed by, and that is a confocal microscope image of the lacunar canalicular system in bone. And so we were able to stain these are the bone cells that live inside the mineralized bone tissue, and then all the little channels that connect them. And we were able to get a stain into that system and then use microscopy to create 3D images that we then used Simpleware to create models of, and including a 3D printed model, which was pretty cool. So looking at that ankle model, just a little bit more detail, we were able to segment, in this case, a cadaver leg image, and looked at different bone compartments. You can see cortical and trabecular bone there with different masks, as well as in the tibia, the same. You can see the red, for example, is the cortical bone. The green is trabecular bone, and then the blue would be marrow space. And then we had a CAD generated IM nail and put those together to create our model. And this is just one example of how you can use those CAD tools to combine medical images and CAD generated devices and do patient specific modeling. And this was that model that was on the screen in that picture of my lab, but you can see this is just taking 2 steps. You can see how the stress gets primarily taken up by the intramedullary nail, and so we were able to get a more idea of how much load goes through the bone and how much goes through the implant. We also looked at ideas for custom spacers or spine cages, and compare the stress distribution if you were to either 3D print or CNC mill a custom spacer based on patient anatomy, how we could spread out stress distribution on the vertebral end plates. You can see a standard kind of donut shaped spacer on the left here in this bright red area where the stress is really elevated. And then the custom spacer, we still do see some high regions of stress, but over a much smaller area of the bone. And we also looked at, okay, if we made this spacer porous and bone grows into that over time, how is that going to change the mechanics of the system? How is that going to change how bone and implant share load? And so for this study, we looked at a specific implant, the fusion cage from Vertera Spine, which has subsequently been purchased by Nuvasive. But they had a spine cage that had a porous coating on the top and bottom surfaces intended to grip onto the bone and have the bone grow in and attach. And so we did a zoomed in model of that. We took a micro CT scan of that implant, and then we got the top of this little cube here is let's say the bottom of the implant here, and then this bottom part is bone. And then using Scan IP or Simpleware tools, we were able to add different layers of bone growth. And we just did that by dilating masks. So you can kind of control the directions that the dilation occurs in Simpleware's image processing tools. And that allowed us to create different layers of bone that fill in the spaces over time. And then we could control the material properties of each one of those layers separately. So we could say what happens as bone mineralizes and matures over time. And then using FEA of that mesh, we were able to look at create this plot on the left that shows the evolution of load sharing, the percent load taken by both the bone and the implant as bone grows in and matures over time. And then the last example here was that lacunar canalicular system. You can see on the left here a confocal microscope image. So very high resolution images, better than we could get in our CT scanner for sure. And we were able to isolate a single lacuna, which is again the holes where the bone cells live in bone, and create a 3D model of that bone cell house, as well as its all the channels that form this interconnected network within the bone. And we did a few things with this. One was I scaled it up 1,000 times, and this cube that you can see right here on the right, I 3D printed it with a clear polymer, and so I've got a 1,000 times scaled up cube with an osteocyte in it that I showed in my class to show what a bone cell actually looks like. And then we use this to investigate the effect of the orientation of that lacuna in the bone relative to loading, and how that affected what we called a strain magnification factor. So how kind of like stress risers, but we were looking at strain in this case. So looking at in its native orientation, and we put a specific amount of compression on the cell. You can see we got about 4 times the little peaks that we saw inside were about 4 times the global strain we put on. But as you tilt that cell over, or that lacuna over, that strain magnification goes up. And so we can see that lacuna that are oriented basically perpendicular to an applied compression get a higher amount of stress magnification or strain magnification. So that allows us to get an idea of like how might cells detect strain, or what level of strain might they be feeling inside the body when you get loaded. And so that is just a few examples again of what we've done in my lab over the years. I've got way more examples. If anybody is interested in learning more, I'm always happy to answer questions or connect you with literature references for anything that we've done here. But then I just wanted to close out and say thank you to my students and collaborators, both at CU Denver, at Georgia Tech, and CU Boulder. None of this work can get done by just one person, and it takes a lot of different expertise to get to this kind of research. And then also just want to acknowledge my funding sources from the National Institutes of Health, the NIAMS and NIA funding bodies within NIH. So with that, thank you, and thanks again to Simon and the Simpleware crew for having me aboard.
Thank you very much, Dana. That's yeah, fascinating tour through both your teaching and your lab, and seeing where Simpleware has been used. Fascinating different length scales as well there that you've been working on.
Thanks.
We'll take a little bit of time now. If folks have any questions, you can put those through in the chat, and we'll try and get to some of those. I know I've got a few things on my mind that I think would be helpful to cover at this point. So, uh, Tom, if you could help me with just sharing slides again. The Simpleware University Bundle. I've mentioned that our aim is to make that readily available to academic institutions. A good question to ask is therefore price. So allow me to tell you about that. We are pricing the Simpleware University Bundle at $1,500 US per year. So that's $1,500 US per year, and that gets you all of the benefits that are listed there on screen. As we've been looking at lots of images from Dana and Dana's lab of the shoulder, of the ankle, of the hip, allow me just to recover uh, uh, the fact that the Simpleware University Bundle, it does not have regulatory clearance. So it's not intended to be used as a medical device. We do offer a product that which is called Simpleware Medical, which does have FDA 510K clearance and European CE marking, and more recently MDR. This is not part of the Simpleware University Bundle, but if you're interested in licensing that for truly clinical facing applications, then please do get in contact with us. But it's worth just being clear on that. Let's think if there's other things that would be worthwhile covering whilst we're here. A question that often arises: is this only meant for US based universities? And that's no. It is. It's available in the Americas, in Europe, in the Middle East, and Africa currently. It's made available through the SARA group from Synopsys in Europe. It's made available through a partner called Europractice, and we would be able to connect you with them for obtaining licensing for an EU academic institution. So I don't see any other questions in at the moment, so let's draw things to a close there. I'd like to say thank you for watching and for your engagement today. Thank you very much to Dana for his time and the presentation he's brought to us. If you want to find out any more about the University Bundle, or if you want to try it, please do get in contact with us. You can book a meeting with me. That's my email on screen, or you can head to the Simpleware Synopsys website. Thank you very much for your attention, everyone. And as I said at the beginning, do please point colleagues, fellow researchers to this resource, and we'd love it to be known more widely as we serve the academic community in this field. So thank you, everyone. Bye-bye.